In the study of quantum field theory simulations, superfluid helium plays a key role in one area mimicking rotating curved spacetime. This research has successfully recreated conditions like the space around spinning black holes inside superfluid helium, using a giant quantum vortex. These experimental results give us important clues to understand and verify phenomena predicted by quantum field theory, such as Hawking radiation that can occur near black holes. Chapter 1: Superfluid Helium and the Giant Quantum Vortex. Superfluid helium is like a shining jewel in the mysterious world of physics. It only exists at extremely low temperatures near absolute zero, and it behaves in strange ways that are completely different from normal materials. One of the most noticeable phenomena is the quantum vortex. Quantum vortices let us see the basic principles of quantum mechanics on a large scale, showing that superfluid acts like a perfect fluid. A quantum vortex happens when there's a swirl in the superfluid, with each swirl having quantized circulation defined by a single quantum state. This blurs the line between the quantum world and the big world, showing us nature's fundamental laws on a tiny scale. The fact that these vortices can form, be observed, and even be controlled in superfluid helium gives physicists a dreamlike laboratory. Recent progress has led to the creation of giant quantum vortices, which are vortices that can contain thousands of circulation quanta, going beyond simple quantum vortices. Stabilizing these giant vortices challenges existing physics theories and deepens our understanding of the universe's fundamental nature. It opens the possibility of simulating the space curvature around black holes, as predicted in astrophysics in a lab environment. The process of stabilizing and studying giant quantum vortices presents many experimental challenges for physicists. This requires highly precise equipment and the ability to maintain extremely low temperatures. However, the insights gained through this process are an asset that can be applied in various fields of physics. Especially, it opens new ways to experimentally explore the connection between quantum field theory and gravity theory. The study of giant quantum vortices opens new horizons in physics, and through the medium of superfluid helium, we can take a step closer to the fundamental principles of the universe. Chapter 2: Introducing research on simulating quantum gravity within superfluids. A study recently published in Nature has introduced an experiment where liquid helium, a superfluid, is cooled to a very low temperature, about 1.95 Kelvin, to create artificial quantum vortices. This experiment observed superfluid quantum phenomena, similar to black hole ringdowns. Here's a breakdown of the main terms you need to know to understand this research. Giant quantum vortex. A giant quantum vortex is a swirl within a superfluid that carries a large amount of quantum circulation. These vortices have more circulation than typical quantum vortices, which is essential for simulating the rotation or curvature of space. In this experiment, the vortex includes thousands of quantum circulations, allowing the lab to recreate conditions like astronomical black holes. Minimally invasive characterization. The research uses a minimally invasive method to study the flow and dynamics of the vortex without disturbing the system. This allows for precise measurements of the interactions between tiny waves and the vortex, while keeping the system's natural state. Analog black hole ringdown signatures. Analog black hole ringdown is a process in the lab that mimics the ringdown of a real black hole. Ringdown is the decreasing vibration or wave that happens after a black hole swallows an object like a star. Replicating this phenomenon in the lab helps us better understand the physical processes around black holes. Superfluid helium He2. Superfluid helium is helium at a very low temperature, showing a superfluid state. In this state, helium flows without viscosity, meaning it can move without friction, and it can climb up the walls of its container. Superfluid helium is an ideal material for quantum physics experiments, especially for studying phenomena like quantum vortices. Quantum field theory simulations. Quantum field theory simulations use the principles of quantum mechanics and the theory of relativity to explain how particles and fields interact. This research uses superfluid helium to simulate quantum field theory in curved space, especially in rotating curved spaces, to replicate phenomena observable in the lab. Now, let's briefly look into the core content of this research. This study shows that giant quantum vortices, like those spinning around stars or black holes in space, can also be created in superfluid helium. Usually, these vortices are very unstable and disappear quickly, but the researchers managed to stabilize them, making them like massive vortices in space. This allows us to create an environment, like the rotating spaces in the universe, right in the lab. To study these vortices, the researchers created tiny waves on the surface of the superfluid. To see how the vortices behave, this method minimally invasive characterization allowed them to look deeply into the mysterious world of vortices without disturbing them, like observing wild animals with a sophisticated camera. They also looked for a special kind of echo analog, black hole ring-down signatures in superfluid helium, like what's expected near black holes. These echoes are like the vibrations in space when a black hole swallows something like a star, helping us understand black holes and other mysterious phenomena in the universe better. Lastly, this research shows how superfluid helium can be an excellent laboratory for exploring the fundamental laws of the universe, especially through experimenting with complex theories like quantum field theory. Quantum field theory simulations. Chapter 3: Superfluid helium in quantum field theory simulations. A new window to the future. Quantum field theory is essential for understanding particle physics and the universe's fundamental structure. But, because of its complexity and abstract nature, experimenting with and proving quantum field theory has always been challenging. In this setting, superfluid helium gives us a unique and powerful tool to directly observe and explore the deep principles of quantum field theory in the lab. Superfluid helium is a special state of matter that appears at extremely low temperatures, close to absolute zero. This amazing material loses all viscosity, allowing it to flow without friction inside containers and even climb up the walls. Thanks to these unique characteristics, superfluid helium provides an ideal environment to observe quantum mechanical phenomena on a larger scale. Quantum vortices formed in superfluid, for example, perfectly demonstrate quantized circulation, a core concept in quantum field theory. One key role superfluid helium plays in quantum field theory simulations is mimicking rotating curved spacetime. In this research, we successfully replicated conditions like those around rotating black holes within superfluid helium using giant quantum vortices. These experimental results offer crucial clues for understanding and validating phenomena predicted by quantum field theory, such as Hawking radiation that could occur near black holes. Although using superfluid helium in quantum field theory simulations is still in its early stages, the potential this methodology offers is immense. For instance, complex vortex patterns created by manipulating quantum vortices in superfluid helium could help expand our fundamental understanding of quantum mechanical states. Moreover, these experiments could lead to a better understanding of the interactions between quantum mechanics and general relativity, potentially advancing the development of quantum gravity theories. Today, we introduced experimental research that utilizes giant quantum vortices in superfluid helium-2 to simulate quantum gravitational phenomena around black holes in the lab. The idea of replicating phenomena occurring around distant black holes in a lab using superfluid, which share similar physical structures, is incredibly creative. That's all for Science Catch with the same.